Can you see the slides?
Yeah, nice. Thank you, leader.
Yeah, very good. So this is indeed a talk about rate-splitting multiple access with application in 6G. This is actually an area that we've been working on for the past 5 years or so. So I have to thank my PhD students and postdocs and many collaborators, an increasing number of collaborators who have been we have started working on this in the past few years. You have a long list here, non-exhaustive list of collaborators. And so during this 1 hour, essentially, I will talk about the following. I will talk about existing multiple access techniques relatively briefly. And then I will introduce rate-splitting multiple access, tell you how it works. And then we're going to look at applications of rate-splitting multiple access in numerous different scenarios and the interplay between rate-splitting multiple access and other technologies. Look at physical layer design and then conclude. Right, so multiple access, why do we use multiple access? Is simply because wireless communication systems are, by default, they are multi-user systems. And so the question is, how do we serve those multiple users? There are two really key building blocks. We have the downlink scenarios and the uplink. So the downlink is what is called broadcast channel in communication information theory. And the uplink is what is usually called multiple access channels in communication theory. So in this talk, we'll focus on the downlink setting, but the techniques that of rate-splitting multiple access can be used in the uplink as well. Right, so what do we do when we look at multiple access? Here in the downlink, we have a transmitter, potentially equipped with multiple antennas, here M antennas, and we have multiple receivers. So receiver user 1 to user K. In this example, those are single antenna receivers, but they could be multi-antenna receivers. And we transmit multiple streams, independent streams, from this transmitter to those K receivers. And the question is, how do we do that? What kind of techniques can we come up with in order to serve those K users? And so this is what this whole talk will be about. Now, to compare those different techniques, we have to come up with a metric. And so the typical metrics in communication is to look at rate. You can define it as a per user rate or a weighted sum rate or just a sum rate, so the sum of the rate, or maximum rate, so you maximize the minimum rate among all those users, and so on. And typically in the high SNR regime, as you increase the SNR, those rates can always be written as something like this. Rate of user K here would be something dk multiplied by log 2p, where p is the SNR. So we have the SNR here in dB, and we have the pre-log factor of the SNR is dk, and this is what is called degrees of freedom or multiplexing gain. So this is the slope of the rate as a function of the SNR. And so if you have, for instance, a sum rate, the sum of the rate across those K users, you have now some degrees of freedom or some multiplexing gain that would still be written as essentially the slope of the sum rate versus the SNR in dB. And so typically, if you have two communication strategies, for instance, here, one in red and one in blue, with for a setup with, for instance, 2 users and 2 transmit antennas, the one you would prefer is naturally the one that actually has the largest degrees of freedom, because that's the one that will lead to the fastest increase of the rate versus SNR. So in other words, as you increase your SNR by 3 dB, if you have a strategy that has a larger DOF, the sum rate or the per user rate or the maximum rate will always increase faster with the SNR. So the red strategy here would be better than the blue one. So in this talk, we'll talk about different metrics. We'll talk about sum rate and maximum rate, but we also come back and talk about multiplexing gain. So you can just think about this as the slope of the rate versus the SNR. The larger the slope, the better it is. Right, so what does information theory tell us? if we have single antenna system, so this what I call here, or what is called SISO broadcast channels. So we have single antenna at the transmitter and at the receiver. We know that the user can be ordered. It can be ordered according to this channel strength. And so the capacity achieving strategy here is well known by Tom Covers in the 1970s, is superposition coding with successive interference cancellation. An alternative strategy, if we have single antenna, is to use dirty paper coding. That is by Costa in 83. Now, if we have multi-antenna system, so either multiple antennas at the transmitter or actually multiple antennas at both ends, then the system becomes a bit more complicated because users cannot be ordered based on its channel strength. And so that's the reason why this kind of strategy of superposition coding with successive interference cancellation is not capacity achieving. It leads to a performance loss. And the only known capacity achieving strategy in this setup is dirty paper coding, by shown in this paper in 2006. So this is true, but keep in mind, this is under the assumption that the channel state information is perfectly known. So those K vectors here would have to be perfectly known at the transmitters and the receiver. Right, so what do we use in practice? Well, we don't use dirty paper coding. We use something else. So you have orthogonal multiple access, where essentially you eliminate any form of multi-user interference simply by allocating users to orthogonal resources. So you can have this in the time domain, so that's TDMA, different users in different time slot, in the frequency domain, or you can have in the code domain. So TDMA, FDMA have been used heavily in 2G, CDMA in 3G. And then we have in 4G and 5G, we have OFDMA. So we create using OFDM a grid, a time frequency grid, and then each chunk of time frequency resource is allocated to one user. Right, we have also SDMA. So SDMA is a space division multiple access. And the goal here is to use the spatial domain to form some beam and separate users using those beams, or what is called also precoding. And so this is heavily used in 4G and 5G. This is the main multiple access in 4G and 5G in combination with the OFDMA, and is used in multi-user MIMO, massive MIMO, millimeter wave, network MIMO, and so on. So the idea is the following: you have multiple antennas at the transmitter, you create multiple beams, and each user is served by essentially one beam. And the important thing is what you do at the receiver. The receiver, you simply do nothing. You treat any residual interference, you treat it as noise. And so what you do is that hopefully by forming those beams, by doing precoding, you manage the interference sufficiently well, such that the interference at the receiver is quite negligible. And so this is what the architecture looks like. We have K user that we want to schedule. We encode those K message W1 to WK. So we encode and then modulate them into K streams, K independent stream, S1 to SK. And then we precode each of them, each of those K streams. And so we create essentially effectively beams for each of those K streams. And at the receiver, each receiver decode is on stream by treating residual interference as noise. So that's a very big important thing here, is to treat interference as noise. Now, if we go to we look at the benefits, the pros and cons of these techniques, is the first benefit is actually very good to exploit the degrees of freedom benefit of multi-antenna system when we have perfect CSMT. And it can do this by having a very low precoder and receiver complexity. The drawback is that it works well when it's underloaded regime. So when we have fewer users than the number of antennas, it works not as well when we have an overloaded regime, when we have many, many users that we want to serve. It works well when the users are quite separated from each other. So if actually the channels for those different users are quite orthogonal, semi-orthogonal or orthogonal, then this kind of strategy works really nicely. But otherwise, you can have some performance loss, especially if you have, for instance, the channel strength disparity between the users is quite large, and is not robust to imperfect CSIT. So when we don't know the channels accurately, the transmitter, then the performance drops. Again, important property is to fully treat any residual interference as noise. That's the key. Now in NOMA, is quite different because in NOMA, we use the power domain to break the orthogonality, and we use the superposition coding with SIC architecture. So here is an example in a single antenna setup. We have two users that are superimposed in the power domain. And at the receiver, what we do is that we have one good user with a good channel, and we have one weak user with a weak channel. And the way NOMA works is such that the good user, the strong user, will decode the message of the weaker user. So the user one here that is closer to the base station will fully decode the message of user two, right? So you can view this as fully decoding interference, essentially. So this has been looked at in 5G. This is well known in communication theory for a long time, for 50 years, but it's been looked at in 5G as a study item, and it was discontinued as a work item. Because again, we're not sufficiently, we're not significant enough. Now, there's been a lot of work on that and the combination of NOMA with multi-antenna. So here is an example of how you can combine NOMA with multi-antenna. You create essentially groups. So you have K users and you pair those users to form groups of users. And in each group is served by a certain beam. And in each group, you actually apply the NOMA principle. So one user will decode the message of all the other users in that group. So for instance, here, this user one here will decode the message from user two all the way to user G. So here again, what is the key is that one user fully decode the message of other users. So in other words, one user will fully decode the interference created by the message of other users. And we have to be very careful when we do this, because this leads to actually an inefficient use of multi-antenna and SIC receiver. And this is something that is, to a big extent, is completely overlooked in the literature. And I will show you this later on when we see some of those analyses. Right. Right. So what is the advantage of this kind of techniques is that it's really designed for single antenna systems. And this is where it was originated, is really for single antenna systems. And that's where it's capacity achieving. Once you apply this in multi-antenna settings, then things do not go very smoothly. It works only in very specific settings when the channels of the users are aligned. It leads to very high complexity at the transmitters and the receiver with multiple layers of SIC, and it leads to an efficient use of the multi-antenna that leads to loss in degrees of freedom and therefore rates in both perfect and imperfect CSIT. Key property here again is to fully decode and cancel interference created by other users, right? So you see the two extreme. SDMA on one hand, you treat interference as noise. NOMA, you fully decode interference. Right, so what about rate splitting multiple access? So the first thing we have to notice is that this whole discussion about orthogonal versus non-orthogonal is really not the problem. If you look at techniques like SDMA, in 4G and 5G, this is already a non-orthogonal techniques where users interfere with each other depending on the way the precoders are designed. So this is really not the problem. The problem is how the interference is managed. And so in orthogonal multiple access, there is no interference simply because you use orthogonal resources. In SDMA, you treat interference as noise. In NOMA, you fully decode interference. What we know from information theory is that treating interference as noise is okay as long as the interference is weak. Fully decoding interference is okay as long as the interference is strong. But in between, none of those techniques are actually the way to go. In between weak interference and strong interference, what we need to do is to partially treat interference as noise and partially decode interference. And so you can view this, you can think about this now in terms of multiple access. If you have SDMA, it would work well whenever the interference is relatively weak compared to the noise. That's really the scenario where actually that works well. If the interference becomes non-negligible, so you have a medium interference regime or strong interference regime, then the SDMA performance will drop. If you have NOMA, this is really tailored for scenarios where actually you really have strong interference that you have to decode. But if it's medium interference or weak interference, again, the performance will drop. with rate splitting multiple access, essentially you rely on this principle. You partially treat interference as noise, you partially decode it. And by doing this, you can adjust how much interference you decode, how much you treat it as noise. And so you can really bridge the treat interference as noise on one hand and the fully decode interference on the other hand. That's why it's a strategy that actually helps you to really accommodate all form of interference regime, from the weak to all the way to the strong. Right, so this is a general, and I will show you why it's general, flexible and robust multiple access strategy that builds upon the concept of rate splitting that was originally invented by Carlisle in 1978 and used in a specific scenario, which is the single antenna interference channel. And so what rate splitting does, what rate splitting multiple access does, it uses this concept of rate splitting, but now use this in the multi-antenna settings, not necessarily for interference channels, but for the broadcast channels that we are interested in here. And so what I will show you is actually rate splitting multiple access is general in the sense that SDMA, OMA, NOMA, and other forms of transmission like multicasting are just sub-strategies of this RSMA framework. And rate splitting multiple access can be viewed as a bridge between SDMA and NOMA by bridging the treat interference as noise strategy and the fully decode interference as noise. And how we do that is by partially decoding interference and by partially treating interference as noise. And this is through the use of a message split that we'll show you. So this is the basic architecture of RSMA for a two-user setup. So we have two users that we want to schedule with. So we have two messages, W1 and W2. W1 intended to user 1 and W2 intended to user 2. And we have at the receiver here, we have two receivers that I will explain in a minute, where we have here the receiver of user 1, and we have the receiver of user 2 that actually is the same as the receiver of user 1, similar architecture. So what do? We take those two messages, and instead of encoding those two messages directly into two streams, as we would have done, for instance, with SDMA or with NOMA, what we do here is that we take those two streams and we split them. We split them into a WC1 and WP1. So W1 is split into a WC1 and WP1. And similarly for W2, we split into two parts, right? So this is the message split part. Then we take the two parts here and we combine them into a new message WC. And essentially now we end up with three messages, WC, WP1, WP2. Then we encode and modulate those three messages into three streams, SC, S1, and S2. The WC is what is called a common message, and SC is a common stream. S1 and S2, what we're going to call private stream. So we go from two streams here, from two messages, W1 and W2, to three streams, one common streams and two private streams. And then we pre-code them. So we use classical linear pre-coding. So what we end up with is a transmit signal that is PC multiplied by SC, the precoder of the common stream multiplied by the common streams, and then the precoder of the private streams multiplied by the two private streams, right? So from two messages, we create three streams. Now, what do we do at the receiver? At the receiver, both receiver will first decode the common stream. So both receiver will decode SC. And then we'll perform successive interference cancellation. So user 1 will actually decode SC, will retrieve the message WC from SC, will retrieve from SC the part that is intended to himself. So user 1 is interested in WC1. So we will recover WC1 from this common message. And then we'll perform SIC. So we'll perform re-encoding, pre-coding, and interference cancellation, and then decode is private stream S1. So what we see here at the receiver is that user 1 tried to retrieve these two parts, WC1 and WP1. And to do that, receiver one, user one, has to decode the common stream SC to retrieve WC1, and it has to decode the private stream S1 to decode WP1. And this is what we do here. We retrieve WC1, we retrieve WP1, or estimate of WC1 and WP1. And then by recombining those two, we actually obtain the original message that hopefully is the same as the one that was transmitted. User two does the same thing, but instead of retrieving, user two will retrieve WC2 and WP2 from the common stream and the private streams. Right, so why is this called rate splitting? Is because we have this message split, and because the rate of a given user has been split into two parts. So what is the rate of user K? Is the rate of its private part, so SK, plus part of the rate of the common stream. So the rate of user one will be part of the rate of the common streams, because part of this common stream carries WC1 that is intended to user one, and the rate of the private stream S1, because that carries the private part, right? So this is where the rate splitting comes in. So how does that relate to SDMA and NOMA? So to see this, well, we can simply think about SDMA. What is SDMA? SDMA is taking a message and encoding it directly into a private stream. So I take W1 and I encode W1 directly into S1. I take W2, I encode W2 directly into S2. So in SDMA, I don't have a common streams. I don't split the messages. So if you like, W1 is not split into WC and WP1. I allocate, in other words, a zero power to the common stream SC. So you can simply turn it off. And what you end up with is just two private stream S1 and S2 that are pre-coded. Where is NOMA? In NOMA, remember that one of the users has to decode the message of the other users. So how can we do this here with this rate splitting architecture? Well, I can simply do that by allocating zero power to S2, for instance. So I will allocate the zero power to S2. And so I will have only two streams that are transmitted, S1 and SC. I have two streams that are transmitted, S1 and SC. Now, those are not the same stream as what we had here. Here we had two private streams that S1 is decoded by user one, S2 is decoded by user two, and any interference between those two is treated as noise. Here, what we do is different. We encode the message of W1 into SC, the message of W1 into S1, and the message of W2 into SC. So why we do that? Because the message of W2 of user 2 has to be decoded by both users. Remember that in NOMA, one user decode the message of the other user. So if I encode W2 into SC, that means actually both users will decode W2. So the strong user, user 1, will also decode the message of user 2. So this is what we do. We have W2 is encoded into the common streams and W1 is encoded into the private streams. And so in NOMA, we have a common stream as well. A common stream is a stream that actually is not necessarily intended to both users, but has to be decoded by both users. And this is exactly what we have in NOMA. SC is decoded by both users, but the content of SC here is actually intended to user 2 only. But nevertheless, user 1 will still decode it. Right. So a common stream is not the same as a multicast streams in the sense that the multicast streams is generally intended to multiple users. So, but a common stream here is actually intended to a subset of the users, but has to be decoded by all for interference management purposes. Right, so another way of seeing that is by looking at the mapping of messages to streams. And so in this architecture, what we have is 3 streams. And the question is, how do we map the messages or the bits to those 3 different streams? So in SDMA, we take W1 and W2, and we encode this into S1 and S2. In NOMA, we take W1, we encode into S1, and we take W2, we encode into SC, to the common streams. And if you have OMA, we simply encode W1 into S1, and we don't transmit anything into S2 and SC because we just transmit one user at a time. And if you do multicasting, essentially, you will do a form of transmission so that all the users, all the messages has to be decoded by all. So the message is decoded by all. Now in rate splitting, we split so that part of the message of user one is transmitted onto S1, and part of the message of user one is transmitted into SC. So WP1 is intended to user one, WC1 is intended to user one. But they're both transmitted on different streams. S1 decoded by user one only, SC decoded by both users. Now, the difference between those two streams is the following, those three streams. Anything in blue is treated as noise. So whenever you have interference between those two streams, you treat interference as noise. Whenever you have something that falls into SC, is decoded by both users. Okay, so we see from this that by adjusting the content of the private streams and the common streams, we actually can boil down to SDMA or to NORMA or to OMA or to any other forms. Or you can have something that is strictly different than any of those multiple access strategies. So here you see from this very simple example that rate splitting is actually a more general framework that encompasses SDMA, OMA, NORMA, and multicast as a particular case. So how do we split those messages? What does that mean at the bit level? So let me give you an example here where imagine I have 4 bits to transmit for user 1, and I have 3 bits to transmit for user 2, right? So those 4 bits can come from actually a message set that contains 16 elements and 8 elements for user 2. And so the way the message split works is the following. I have 4 bits I want to transmit to user 1. If I'm doing SDMA, for instance, I will encode those 4 bits into a 16 QAM, for instance, 16 QAM symbol. And then here for user 2, I will transmit, for instance, an 8 PSK symbol, right? Now, what we do is not that. We first split the messages into 2 parts. So we take, for instance, 2 bits of W1, and this goes into the common part. This goes into WC1. And the remaining 2 bits here would go into the private part. So we take the first 2 bits that goes here, and the other 2 bits go there. Then for user 2, we take, for instance, 1 bit that goes into the common part and 2 bits that goes into the private part. And then we take WC1 and WC2, and we combine them together into a common message. So I have 2 bits for user 1 here, A1, A2, 1 bit from user 2. So I have 3 bits. And now I can encode and modulate that. So what I would end up with is, for instance, here, I have 3 bits, so I can map this onto 8 PSK symbol, for instance, for the common stream. So here I would have 8 PSK, for instance. S1 would actually encode the private part. So I'm going to have 2 bits. So for instance, I use a QPSK here. And here I have 2 bits again. And so I use a QPSK. And so each receiver, what we'll do, user 1 will decode here 8 PSK symbol. And from there, we'll retrieve the bits. User 1 will retrieve the bit that actually is intended for himself. So WC1. So we'll retrieve those 2 bits, A1 and A2. And we'll discard B1 because that's not something he's interested in. Right. So what if we have K users? Well, the first and the simplest architecture is the following one, is you just have K users, K messages, W1 to WK, that you actually split into a common part and a private part again. So now we have K common parts here, and we have K private parts. And we combine them into one common streams, and we have K private streams. So what we end up with essentially is a transmit signal vector that is one common stream SC multiplied by a common precoder plus K private streams that are each multiplied by its own precoder. So we go from K messages, we generate from K messages, we generate K plus 1 streams. One common stream that is decoded by all those K users, and K private streams that are decoded by each individual user. So user 1 will decode SC will decode is the common stream to retrieve the part of the common stream that is intended to user 1. And then we'll decode using SIC, we'll decode the private streams S1 and we'll retrieve the private part. And then recombine the two, the private and the common, into the original message. So where is multi-user MIMO here or SDMA? Well, again, is obtained by just turning off SC, by allocating 0 power there. So if you design your system and you optimize this, if you allocate 0 power to SC, automatically it boils down to what you have in 5G, which is classical multi-user linear precoding. NOMA, as I presented before, is not a subset of this one-layer rate splitting strategy. If k is strictly larger than 2, is a subset if k is equal to 2, but if k is larger than 2, is not a subset. That will comment on this later on. Right. So the important thing here is that we had those, aside the rate splitting and the common stream, we had here k private messages here that are encoded independently into k private streams and then linear precoded. What we could do here is to do some form of non-linear precoding instead of linear precoding. So one strategy is the following, and this is what is called here dirty paper coded rate splitting, is to, instead of encoding those k private parts into independent k private streams and then linear precode them, what we do here is that we use dirty paper coding. And so why is this interesting? It's interesting because we know that DPC is capacity achieving when we have perfect channel state information at the transmitter. And so what that means is that if we use this architecture, when we have perfect CSIT, it means that if you optimize the system, you should not allocate any power to the common stream, because we know that this part here is capacity achieving. So there is no need to split the message when you have perfect CSIT and you have this architecture. But once you go to imperfect CSIT, then the capacity is not known. And what we can do with this architecture is outperform DPC. And so the outperforming DPC will come from the fact that now actually we allocate a non-zero power to the common stream that will help to manage the interference that actually is due to, that is coming due to the imperfect CSIT. So I will show you some results of this later. Right, so there are some more advanced architectures where you do multiple split of the messages and you can have more than one SIC at the receiver. This is what is called two-layer or hierarchical rate splitting or generalized rate splitting. The bottom line is the following, is that if you do one-layer rate splitting, which is the simplest architecture I showed you, SDMA and multicasting are just subsets of that architecture. You can do something slightly more complicated, which is a two-layer rate splitting. And then you can have a general approach of the RSMA that will always encompass those different type of rate splitting in SDMA architecture on one hand, and the NOMA architecture on the other hand. And so this bubble I showed you specifically for the two-user case, but you can actually show that actually this holds for a k-user scenarios once you go for the generalized rate splitting framework. Now, what is very interesting is this one-layer rate splitting architecture, because it's very simple. It's just one SIC. So we will go into that. I will show you some simulation results, but I want just to summarize the benefit that we see from these rate splitting architectures. So the property is really to partially decode interference and partially treat interference as noise. And by doing this, you really bridge the extremes of NOMA and SDMA. And that gives you the performance benefit, the flexibility, the robustness to imperfect CSIT, and the flexibility to different interference regime, whether it's weak or strong. So it encompasses SDMA and NOMA as special case. So as a consequence, the rate of RSMA will always be better than SDMA and NOMA. And we can show from an information theoretic perspective that actually the one-layer rate splitting architecture I showed you is actually information theoretic optimal in terms of degrees of freedom when we have both perfect and imperfect CSIT. So the key novel part here is really the imperfect CSIT. We can show that actually is information theoretic optimal in terms of degrees of freedom. We can show that actually it copes with any user deployment, whether you have the users are aligned or they're orthogonal, whether they have a diversity of channel strength or not, whether you have CSIT inaccuracy, whether you have different network loads, whether it's overloaded or underloaded. And you can have a much lower computational complexity and receiver complexity than NOMA schemes, because you can rely just on one SIC at the receiver. Now, you can argue the drawback is that the encoding is more complicated, because instead of having K streams or K message that you encode into K streams, now you have a K plus one stream. So you have an additional stream that you have to encode that leads to a slightly higher encoding complexity. I think not a big deal for base station nowadays. Right, so let me show you some results, different metrics. So this is a DOF enhancement. So the slope is increased. So this is a scenario where we have imperfect channel state information at transmitter. And I just want to show you that the increase in DOF. So this is the blue one is what you would get with SDMA. The red one is what you would get with rate splitting multiple access. You get 50% gain in terms of slope when you have a 2-user, 2-antenna systems. If you go here for 4 antenna, 4 users, you get an increase from a DOF of 2, you go to a DOF of 2.5. But this is when we have imperfect CSIT. Can you do better than that in terms of slope? No, you cannot. So the slope in red here is the actually information theoretic optimal. You cannot do better than that. So the rate splitting reached the optimality. So it's optimality in terms of degrees of freedom. Right, so let's look at DOF versus the number of users, number of SIC first. So we look at two metrics. So I have some multiplexing gain. So this is the pre-lock factor or the slope of the sum rate, if we like. And we have a max min fair DOF. So I'm looking at the minimum rate among those K users, and I'm looking at the slope of this minimum rate as a function of DSNR. So those are two different metrics. Some DOF here would really favor trying to maximize the throughput in the systems. Max min fair DOF is really trying to be fair among all the users. And I have two figures here. Left is with perfect CSIT, right is imperfect CSIT. Those are theoretical results, proved mathematical proof. And each point here corresponds to the actual and true multiplexing gain or DOF that is achieved by each of the schemes. So you have some in blue here, and red refers to the max min multiplexing gain. So what do we see here? X-axis is the number of SIC layers. So we have here, if you don't need any SIC, you do SDMA or multi-user linear precoding, you treat interference as a noise at the receiver, so no SIC is needed. What you see is that in terms of some multiplexing gain, it works well. In terms of max min fair, it doesn't work well. In this example, we have 4 transmit antennas and 6 users. If you go to NOMA, there are different types of NOMA schemes depending on how you pair the users in each group. So here, for instance, I have 3 groups and 2 users per group. Here I have 1 group and 6 users in that group. And so what we see here is that those 2 NOMA schemes perform very differently. One performs better in terms of some DOF than the other one, while the other one performs better in terms of max min fair DOF compared to the other one. So depending on the number of users per group, the performance can change quite significantly. The bottom line is, as you increase the number of SIC, you see that your sum DOF decrease. You start from SDMA that does not need any SIC, you have good sum DOF, then you increase the number of SIC, you get something that is worse, and you go to even higher number of SIC, and you have an even worse sum DOF. So in other words, you increase the complexity of the receiver, and what you get in return is a slope of the sum rate that decrease. That's definitely an inefficient design. On the other hand, if you do 1-layer rate splitting, you have a scheme that relies only on 1 SIC, and you get a sum DOF that is either equal or better than any of these other schemes. As you move to imperfect CSIT, the gap is even larger. You see that actually the performance in terms of max min fair DOF and sum DOF of the 1-layer rate splitting is significantly larger than what you get with any of the other schemes, despite the fact that you have a much lower complexity than NORMA, for instance. Right, so what about DOF versus the number of users? So one of the argument when we go for NORMA schemes, or when you go to massive access, is to try to serve a larger number of users, right? So let's look at that here, where I'm looking at the max-min fair DOF. So I'm looking at again, the slope of this max-min rate as a function of the number of users that I have in the system. And so what we see here is that if I want to aim at having a max-min DOF of 0.1, so I want the pre-log factor of the rate here to be 0.1, for instance. How many users can I serve while still maintaining a max-min fair DOF of 0.1? When we see that if you use NORMA here in yellow or SDMA here in purple, essentially, once you have a number of users that is larger than 6, then the DOF drops. So for instance, I'm not able to serve 8 users. My max-min fair DOF would be equal to 0. So if I want to serve, maintain 0.1 of max-min fair DOF, I would have to actually serve maybe 6 users or less with these NORMA schemes and these SDMA schemes. If I use a NORMA schemes here with only one user, one group, so one group of K users, I can actually afford to have a max-min fair DOF of 0.1 and serve 10 users. That's the maximum number of users I would be able to serve, is 10 users to maintain a DOF of 0.1. What do I need to serve 10 users when I have one group? I need 9 SIC. So if I can afford 9 SIC at each receiver, NORMA with one group here would be able to actually maintain a quality of a DOF of 0.1 with 9 SIC. What we do with rate splitting is here, you end up with serving 15 users while maintaining a DOF of 0.1, and you do this with only 1 SIC, right? So you see here again, you can serve more users with a significantly lower receiver complexity. As you move to imperfect CSIT, the gap becomes even more significant, and that comes from the fact that rate splitting is actually information theoretic optimal in terms of DOF when you have imperfect CSIT. Right, so let's look at some precoder design before looking at some real rate performance. So I mentioned this system model where we have the common stream and the private streams. I know the question is obviously, how do I design this common stream and these private streams? I may need to optimize this. So how do we optimize that? Is by looking at convex optimization. So here I have one common precoder and K private precoders that I need to design. And the rate, and I'm subject to a power constraints, so that is total power of the common plus the K private. And then the rate of a given user, as I said, has been split into 2 parts. So I have the rate of the private part. So for user K, that would be the rate of SK here. And then I have part of the rate of the common stream. So part of the rate of SC is actually intended to user K. So CK here, if you like, is the rate of the sub-message here of user K, in a way. So the rate of user K would be the sum of the part of the rate of the common stream plus the rate of the private streams. What are those 2 rates? How can we express them? Is as following. The sum of those CK, this will be the rate of the common stream. So the sum of the rate of each of those sub-messages here will be the rate of the common stream. And this will be the rate of the common streams. And the common stream has to be decoded by all. So that means actually I need to transmit this common stream such that is supportable by the channels of those K users. And that's why I have a minimum here. The minimum here means that the rate of the common stream need to be adjusted so that it can be decoded by all those K users. So RCK is the rate that the channels of user K can support when it decodes the common streams. So the common stream, the rate that the channels of user K can support when it decodes a common stream is log2 1 plus SINR. When I decode the common stream at user K, I have the signal power of the common streams divided by the interference created by those K private streams. So that's the rate at which user K could decode the common streams. User K can then decode its private streams by removing the common streams. So if it removes the common streams, the only interference that user K will see is the interference coming from the K private streams. So user K here will still see interference from S1 all the way to SK with J different than K, different from its private streams. Right? So from those two expressions, now we can have the rate of the common streams, the rate of the private streams, and we can do some optimization. So here's an example of how you can formulate a weighted sum rate problem with perfect CSIT. What do we have to optimize here? We have to optimize the precoder, but we have to optimize those the split of the messages. So we have to optimize those CK as well. Depending on how I allocate CK, do I allocate more to user 1, to user 2, to user 3, and so on, then the rate of each of those users will change. And so this is important when we have a weighted sum rate, for instance. We try to maximize the sum of the weight of the rate of user K. And the rate of user K, again, is given by the CK plus this RPK. And I'm subject to a few constraints. The first constraint is the following. That means actually the common stream has to be decoded by all. And this is this constraint here. That's what it says. We have a power constraint that is given by this. We have potentially a quality of service constraint that says that the rate of user K should be larger than a certain threshold. This is when I want to guarantee quality of service. And the portion of the rate that the portion of the common streams that actually allocated to user K has to be positive, obviously, cannot be negative. And so this can be solved using successive convex approximation or weighted MMSE using alternating optimization, and can be extended to other framework where we have imperfect CSIT with bounded inputs or unbounded inputs with other metrics like max min rate, energy efficiency, and so on. So let me show you some results. So here you have a perfect CSIT, weighted sum rate maximization, 2 users, 2 transmit antennas, 20 dB SNR for the strong users and 10 dB SNR for the weaker user. And you have in blue DPC. So this is the capacity region. So you cannot get better than that. Red one is 1 layer rate splitting. You see them quite close to the capacity region. Yellow one is NOMA, and green one is multi-user linear precoding as you have in 4G or 5G. Right, so you see that the rate splitting outperforms those two schemes and come closer to the capacity region. Still weighted sum rate, but now I have quality of service constraints. So I want to make sure that each user gets a certain minimum rate. So here I have a quality of service constraint. And I have here 2 transmit antennas and I have 10 users and I want to serve those 10 users. Because I have many users and few antennas, multi-user linear precoding or SDMA does not work well, because there is too much interference left in the system. I cannot simply treat it as noise. The interference is not negligible compared to essentially the noise. NOMA has a small performance enhancement, but to have the small performance enhancement, you have a price to pay, which is having 9 SIC. So you have 10 users, so each user should actually implement 9 SIC layer, very high complexity. Pink one is 1 layer rate splitting. You get a much higher weighted sum rate, and you have only 1 SIC at the receiver. Right? The reason, again, why we have this gain is that we are not in a regime where we treat interference as noise. We are not in a regime where actually we fully decode interference. We actually find out what is the sweet spot to really treat interference as noise, but partially decode interference. And that gives you the performance enhancement and the decrease in the number of SIC. Here we have max-min rates. So we try to maximize the minimum rate among those K users, 6 users, 4 transmit antennas. And here you see again that the rate splitting gives you significant performance enhancements over NOMA and multi-user linear precoding, whether you have perfect CSIT or imperfect CSIT. And this comes with, again, one SIC receiver. Right, so here this is rate region with imperfect CSIT. So remember what I mentioned earlier on, when you have perfect CSIT, we know the capacity region, we know it's achieved by DPC. That's the reason why here you cannot get something better than the blue curve. Now, when you go to imperfect CSIT, we don't know what's the capacity region. It's unknown information theory, but we know that rate splitting is a right way to go because it's actually optimal in terms of degrees of freedom. And this is what you see from this figure here. This is a rate region where you have imperfect CSIT. NOMA does not perform well. Multi-user linear precoding or SDMA performs better. And DPC is in blue, performs better than linear precoding. This is expected. But then you have rate splitting that just relies on linear precoding, does not rely on any complicated encoding, and just one SIC, and that outperforms DPC. And you have DPC RS, which is the combination of DPC and rate splitting that outperforms all those techniques. Right? What I want to show here is that those rate splitting schemes can outperform any form of non-rate splitting strategies like DPCs, NOMA, and multi-user linear precoding when we have imperfect CSIT. Right? So it even outperforms DPC. Right, another example here, that is scenario where we have max-min fair, but we have a robust max-min fair. So we have, that means that the channel state information, the CSI errors that we have is bounded within a ball. And if we do a proper optimization, we can optimize the rate splitting compared to SDMA and optimize SDMA, and we can show that the rate splitting offers a significant max-min fair rate enhancement across the whole SNR regime. SDMA will lead to actually some form of saturation because of the imperfect CSIT that will lead to multi-user interference, while the rate splitting will actually have a max-min rate that will keep increasing with the SNR. Right, so you can apply this into many different scenarios now. And this is actually a list of application scenario you can look at that people have started to look at in the past 12 months. So multi-user MIMO with statistical CSIT, quantized feedback, massive MIMO, millimeter wave systems, when you have cooperation or relaying, physical layer security, when you have the intelligent surfaces, multi-cell, CRAN, blah, 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 and so on. So I will not go into all of them, all those applications, but I will choose some of them. And if you're interested, I can provide a list of reference for all those different applications. So first application, FDD massive MIMO. So here we scale up the number of antennas. We have 100 antennas, 12 users, and we have a system that relies on FDD. So you need some form of feedback. And so a traditional way of doing that is to pair users into different groups and to do a form of two-tier precoding, where you use the spatial covariance matrix to separate the users, and then you use a short-term precoder design based on the CSI feedback. Two main issues. First is you can have overlap between the egg and subspace that are spanned by the covariance matrices of those different users, and you have the imperfect CSIT, and those two leads to a performance loss. This is what we see here. If you do this state-of-the-art two-tier precoder, which is in yellow, is here. And if you design a proper rate splitting techniques, you get performance enhancement that is about 40% rate enhancement in terms of some rate here, depending on tau, which is the quality of the CSI. So tau is small here, leads a good quality of CSI. As tau increase here, we have a lower quality of CSI. So you see here, the gain becomes significantly higher when you have imperfect CSIT because of the interference that is left in the system that cannot be managed properly by simply doing a precoding design at the transmitter. Right, if you have a TDD system, then the channel estimation is different, and the problem is there is that you may have pilot contamination. So here what we show is that any pilot contamination leads to imperfect CSIT. And so here, rate splitting can help you again because it's robust to imperfect CSIT. And this is what we show here. If you have your average sum spectral efficiency, will actually increase this with as a function of the SNR, the transmit power, with rate splitting, while at some point it will saturate with the classical massive MIMO. If you increase the number of antennas as well, you see that actually for a finite number of antennas, you have actually a spectral efficiency increase with rate splitting compared to classical massive MIMO, simply because the system becomes more robust to pilot contamination and imperfect CSIT. Right, another problem when you have in massive MIMO, even if it's TDD, even if you have accurate CSI estimation on the uplink, is that you have mobility and latency. So if you have a 10 millisecond delay between the time you perform channel estimation on the uplink and the time you actually schedule the user, then you have a significant performance loss depending on the user speed. And this is what we see here. This is actually throughput. So this is really link level simulation. I will talk a bit about this later on. But the bottom line is the following. You see that with SDMA or multi-user linear precoding, your performance drops very significantly as you increase the user speed. So here we have 32 antennas, really 5G setup, 8 users that you want to serve, and the performance drops because as the mobility increase, you have your CSIT quality becomes worse, and so you cannot manage the interference between the users. With rate splitting, it's more robust. So what you see here is that if you want to afford to have, for instance, a throughput of 6 bits per second per hertz, you can serve users with SDMA at 7 kilometers per hour at most, while with rate splitting, you would can serve them at 40 kilometers per hour, right? So the rate splitting multiple access here helps you maintaining multi-user connectivity, even if you have mobility conditions and a tiny latency between your channel estimation and your actually data transmission. Right, you can do cooperation. So we have, when we have this architecture, we recall that the common stream has to be decoded by both users. So what you can do at the receiver is to enable some form of user relaying or device-to-device communication, where one of the user can actually forward to the other users the common streams in order to help the other users to better decode the common streams. And so this can help improving the performance of cell edge users or users are really low SNR through this cooperative rate splitting. So that combines the benefit of RSMA with a user relaying phase. And we can show that this CRS or cooperative rate splitting then outperform the one-layer rate splitting without cooperation, multi-user linear precoding, NORMA, and any form of cooperation schemes that you have in NORMA. Right, you can use RSMA in a Cloud RAN setup. So in the Cloud RAN, you have multiple remote radio heads like this that are connected to a cloud that performs all the processing. And so what you can do here is that you can do one-layer rate splitting, for instance, here, performs in the cloud, and then you can forward those transmit signal vectors to each of those RH to enable a joint cooperation among all those multiple antennas from those different RH. The challenge in Cloud RAN is that the front haul here, so the link between this cloud and each of those RH is limited. And so what you may need to do is some form additional compression on your transmit signal vector before you actually forward this to each of those RH. Another architecture for CRAN, still based on RSMA, would be to actually, after you split your messages, you encode them, and then you decide which common stream and which private streams would actually be transmitted to which RH. So there you have a resource allocation problem, which common stream and which private stream you transmit on which front haul links. Bottom line, you can show that for a given front haul capacity constraint, for a given quality of those front haul links here, the RSMA will be more efficient in terms of spectral efficiency and energy efficiency than SDMA and NORMA. Right. What if you do integrated communication and sensing? So one of the problems there, or radar sensing, is to make use of the spectrum for radar or for sensing and at the same time communication. And if you actually use radar and communication in the same band, you're going to have interference between radar and communications. And so the question is, how do you find a strategy that achieves the best trade-off between a communication performance and a radar performance and the radar metric? And so here what we show is that if you do classical linear precoding or SDMA to manage the interference between communication users and at the same time trying to form a beam to a target in order to maximize the radar performance, then you achieve a certain trade-off between a communication metrics and a radar metric. And what we can show here is that for a given radar metrics, you can actually improve the performance of the communication by using rate splitting, simply because rate splitting would be more efficient at managing the interference between the communication users, but also between the communication and the radar. And so the common stream here can play an important role to actually enhance the performance of the radar and at the same time manage the interference between the users, the communication users. Right. Another interesting application is non-orthogonal unicast and multicast. So when we do unicast, it's all what I talked about before. So you have a one-to-one. You have one message that is intended to one users, and you transmit multiple of those. When you do multicast, you really want to transmit one message to many users. So this message typically would be intended to multiple users. And so the conventional way of doing that, if you look at those cellular systems like 4G, is maybe to orthogonalize the transmission of unicast and multicast, but this is not very efficient. A more efficient strategy would be to superimpose unicast and multicast. So the problem with that is that if you transmit multiple unicast streams and on top of this you have a multicast streams, you're going to have no interference between the unicast streams, that the same as multi-user MIMO or SDMA, but on top of this you have the multicast create interference to the unicast, right? And nevertheless, this is an important scenario in 5G and 6G, because you end up with more and more mixed traffic or mixed services that requires not only unicast, but also multicast or a combination of them. So here's an example. You have unicast traffic. So one message is intended to this user here in blue, one in yellow, and one in green. And on top of this, you have a multicast message that actually is transmitted to all of them. Right, so how would you do that? Now you have one multicast message to transmit and you have K unicast. One way of doing that is to superimpose on top of those K private streams, K unicast streams, you transmit now the multicast streams. So you superimpose them. And what do you do at the receiver? Now you have to use SIC, and the SIC is used to separate the multicast stream S0 from the K unicast streams. So you need one SIC to separate, to manage the interference between the unicast and the multicast. Now you can do something better. If you have one SIC already, why not using it more efficiently for the dual purpose of separating unicasts here from multicast, but also managing the interference between the unicast streams. And this is what we do here with this rate splitting architecture, where we split those K messages into K common parts and K private parts, but then the K common parts are encoded jointly with the multicast message. So those actually encoded into a super common streams, if you like, that is S0 that is decoded by all the users, but that common streams include part of the unicast streams, but also the multicast streams. And so you still have one SIC at the receiver, and the receiver will decode this common stream S0, will retrieve now the multicast streams, will retrieve the common part, and then will perform SIC and retrieve the private parts, right? So here, SIC is used more efficiently to separate the unicast from multicast and at the same time manage the interference between the unicast streams. But if you have multi-beam system in satellite, for instance, you have also a problem because you have lots of interference between those different beams. And so this is typically modeled using multi-group multicast, where you have multiple users in each of those satellite beams. And in each, and those multiple groups interfere with each other. And so what we show here is that you can use the rate splitting, RSMA, to manage the interference more efficiently. And this is what you get here. For instance, in red, you have RSMA performance. In blue, you have the classical SDMA or multi-user linear precoding, where interference is treated as noise. And you see that you get a significant performance gain across whatever power you use at the satellite. And you have this with perfect CSIT, those are the plane line, and with imperfect CSIT with the dashed line. And so here, rate splitting manage the interbeam interference more accurately, manage the interference coming from the imperfect CSIT, and also despite the specific constraint that you have in satellite, which are they have very tight constraint in terms of power allocation and power use per feed. Right. You can use RSMA in short packet communication as well. So this is an example of sum rate or weighted sum rate versus block length. And the dashed line is actually the performance you would get if you had infinite block lengths. And so this is what we looked at so far. When we had the log2 1 plus SINR, we were assuming we had actually infinite block lengths. This is performance when you have finite block length. So this is in plane is actually, you see the increase when you have finite block length. As your block length increase, the sum rate increase of SDMA and also RSMA. And in the limit of infinite block length, then the red one, the plane line, will actually converge towards the dashed line. But what is interesting is the following one. So you see at this point here, to achieve, let's say, 9.5 here bits per second per hertz, you would need with SDMA infinite block lengths. With RSMA, you will need much shorter block lengths, right? So if you have shorter block lengths, that means you have lower latency. And so here RSMA can be used to also reduce the latency. Right. Physical layer design. So this is all what we looked at is really about under kind of optimistic assumption. We have Gaussian signaling or you have infinite block lengths. But at the end, you need to design the system. So you need to actually go for finite constellations. So not using Gaussian inputs, for instance. And you may have a real channel coding or error correcting codes to use. So this is the architecture of the rate splitting techniques. When you have two users, you need to have the adaptive modulation encoding that relies on an encoder, the interleaver, the modulator, and you do this for the common streams and the private streams. And then you have the receiver that needs to perform the SIC, and to do that, you need to actually first decode the common streams, and then reconstruct it, and then decode the private stream. So you need to design the message split, you need to design the channel code, the channel coding that can rely, for instance, on polo code. So this is what we use here. We use polo codes, interleaver. Then you have the finite constellation, can be QAM, 4 dimensions, 16, 64, 256, as we have in 5G. And then you have the precoder that can be based on the optimized precoders from the optimization, or you can have low complexity precoder design based on some form of zero forcing precoding or regularized zero forcing or something like this for the private streams, for instance. And then you design the adaptive modulation encoding. So if you design all this, then you can have real link level simulations and actual throughput performance. The dash one is the Shannon bound that you obtain with actually infinite block lengths and Gaussian inputs. So this is when you have the log2 1 plus SINR expression, and you optimize the precoders. The plane lines here, the plane curves, are obtained where you have the actual link level simulation with finite block lengths based on polo codes and finite constellations. Throughput, so sum rate maximization, and you see here again that actually the rate splitting outperforms significantly SDMA and NORMA, and even more when we have actually link level simulation and finite constellation. Right, link level simulation when you have multi-group multicasts. So here again, You have the plain one, actually the Shannon bounds, and the dashed one here, actually the link level performance. And you see that here in these multi-group multicast, you get really significant performance enhancement of RSMA in red versus SDMA in blue. And the gap is even larger when you have actual link level evaluation compared to Shannon bounds. So again, significant performance. At the cost of here, RSMA has one SIC. And so there is a higher complexity at the receiver compared to SDMA, but it's only one SIC. Throughput performance when you have mobility. Again, link level evaluation. This is as a function of the number of antennas. So you see you have 4 antennas, 4 users. And then here you have 32 antennas and 8 users. And you see that at some point, the RSMA always outperforms the SDMA. The SDMA saturates. And the reason for this is because of this feedback delay or CSI acquisition delay that leads to an imperfect CSIT and multi-user interference. And RSMA can actually mitigate this multi-user interference more efficiently. And that's why you have the rate or the throughput keeps increasing with the SNR. Right. So just to conclude, the key here is the rate splitting multiple access relies on partially decoding interference and partially treating interference as noise. And this is extremely powerful because it enables you to really breach the traditional treat interference as known as we have in 4G and 5G, and this kind of techniques like NOMA that fully decode interference. And this partially treat and partially decode gives you the robustness in terms of imperfect CSIT. It gives you the flexibility to adjust as a function of the level of interference that is in the network. And it enables you to have a completely general and unified multiple access strategy. So you don't need to look at OMA, SDMA, NOMA, and all those variants. All those one actually sub-strategies of actually this RSMA. And so that leaves some change to the physical layer and the multiple and the MAC, the medium access layer, because now you introduce common streams on top of the private streams. Right, in terms of benefits, what we have observed is spectral and energy efficiency gains, quality of service and fairness enhancement, robustness to imperfect CSIT, which helps to reduce the feedback overhead. So if you have a 5G systems where you have a certain number of feedback bits in FDD, for instance, you can reduce the number of feedback bits because your communication strategy is now inherently robust to the imperfect CSIT. It's also robust to hardware impairment. So phase noise, for instance, creates imperfect CSIT problem. And we have shown that rate splitting is robust to this phase noise. Cope with any user distribution, whether actually they're aligned, not aligned, they have different channels, different path loss or not, and the network load. And you can have a significant lower complexity at the receiver because you can just rely on one SIC at the receiver to get already quite a bit of gain. You could have higher gain if you can afford 2 SICs, for instance, but one SIC gives you already quite significant gain. And then you have a lower latency, as I have mentioned. So you can look at this from different perspective in terms of fundamental limits. What are the fundamental limits that is achieved by rate splitting, multiple access, in terms of interplay with other communication techniques, in terms of interplay with other communication systems, like it does not have to be only terrestrial or RF, it could be visible light, it could be satellite, it could be aerial networks, and so on. And then you have a lot of issues on the standardization and implementation, because some of those, it leads to standardization changes, not significant, but some of them in order to enable these kind of techniques. So how can we do that in beyond 5G and in 6G? Well, we can leverage what we have already in 5G. Lots of things have been discussed on MUST, so multi-user superimposed transmission, which is a form of NOMA. Multi-user MIMO, massive MIMO, COMP, network-assisted interference cancellation, broadcast, multicast, unicast. Those are all study or work items that have been discussed in 5G, and rate splitting will actually build upon all of them, and we leverage the work in all those study and work items. But the missing piece to really enable the full potential of rate splitting is to have this message split. And you can have application in 6G, in EMBB. This is the classical one that you look at when you try to maximize the throughput, but also in low latency communication, as I mentioned, in machine type communication. And you can have new services. I mentioned a bit about joint sensings and communication. You can have also in integrated cellular and satellite communications and so on. So with this, I will stop here and I will answer any question. But before just leaving the floor to the questions, I just want to remind you that we initiated about a few months ago this new special interest group as part of ComSoc on rate splitting multiple access. So you have the link there where we organize tutorial, we organize workshops, special sessions. And I invite you to have a look at the best reading here. We collect all the papers, recent papers, the growing number of papers on the topic. And you have also tutorials where I give a bit longer, 3 or 4 hours tutorials that actually you can watch from YouTube. And with this, thank you very much for your attendance and attention. And I will be happy to answer any questions that you may have.
Thank you, Professor Bruno. It was really inspiring presentation. So just a very quick question before moving through the audience's questions. So this is like this is a portal in Communication Society, especially designed for RS, with all references, like from any publication, from any digital library, or is it specific from IEEE?
Sorry, are you referring to this here?
Yes, exactly.
I mean, this is from is initiated as part of IEEE ComSoc, but this link is accessible to anyone. And the best reading, the papers, the link to the papers are probably from IEEE Explore. If this is what you ask. The tutorials there, you can see the slides are available from the websites, and the links to the videos that come from YouTube. So there's those actually tutorials that actually I have uploaded on YouTube. So it's accessible to anyone. If this is what you ask.
Yeah, perfect. Thank you. So just to read the questions. So the first question is Misonoma case, and this audience gave the page number, which is page number 10. Misonoma case. What is the best way to group the users?
Right. So that's the whole problem with the NOMA, is that if you want to get the best, so for instance here, oops, sorry. Right, so you said number 10, right? So here, so you could have one group and K users in one group. And so what that means is that then the strong user has to decode K-1 messages. So it needs K-1 SIC, or you need to split them into multiple groups. The problem is, whatever you do, you need to optimize those groups. And at the end, the performance will be limited because you force yourself to have always one user to decode the message of the other users. This is an inefficient strategy when you have multi-antenna. And this is the reason why in the past 20 years, when you look at multi-user linear precoding, SDMA, this has never been proposed in 4G and 5G because it degrades the multiplexing gain. And this is really what I want to show here in those figures, is that whatever the way you design here, whatever the way you design the number of groups, whether you have multiple users per group or multiple groups, only one group, you will always have a multiplexing gain that is degraded compared to what you can get simply with one SIC and rate splitting. The fact that you increase the number of SIC layers and you have a performance that decrease is really limitation of the basic principle of NOMA, which force a user to decode the message of another user. This can be shown simply using communication theoretic principle. And if you're interested, I really invite you to look at these very recent papers that we really explain this very clearly, because this is a very major misconception in the whole multi-antenna NOMA literature.
Thank you, Professor. Yeah, this was a question asked by Cheyenne. The next question is from Hamad Yahya. How can we make sure that after LP, there is no overlap of constellation points in the space diagram? Something like ambiguity mentioned right over here.
I'm not sure I grasp, but essentially, so if you take this here, so you're gonna have a constellation point here, you're gonna have constellation point here. Here, if you optimize here, you assume those constellation points are not actually no finite constellation. They actually come from Gaussian signaling, right? So when you look at the actual physical layer design, and so for instance, when we do the design here, whether you use SDMA or you use RSMA, you always have to do adaptive modulation and coding. And so you always have to adjust your modulation and coding rate based on what is supportable by each user's channel. So if you do the optimization based on Gaussian inputs and you optimize your precoder, power allocation to the common and the private streams, then what you may need to do is to find out from that supportable rate, what is the closest modulation and coding rate that I can support. So you can need to match that rate to a certain modulation and coding rate. And in that step there, you need to actually, you need to play with the link adaptation in a way. So this is what you do automatically to maximize the rate of the transmissions. And so by doing so, you will be able to decode the common streams. It may be imperfectly decoded sometimes, but that's okay. And then you have the private streams. So you may have error propagation, but by adjusting the modulation and coding rate of the common and the private streams based on your feedback, then you can you can find what is the most suitable way to maximize your throughput.
Next question, thank you, Doctor. Next question is from Rafael. Although uplink is not the focus of the presentation, how can RSMA work in uplink when users cannot cooperate to build a common message? Moreover, is there any promising scenario for RSMA uplink? Please elaborate on that.
Right. So in the uplink is the capacity is well understood there, because you can achieve. So if you have a 2-user case and you have, let's say, single antenna transmitters and you have multi-antenna receiver, the capacity region is known. This is a pentagon. And so you have 2 corner points that are obtained by simply having each user transmitting its own stream, and any points in between those 2 corner points would be achieved by doing time sharing. So you have this pentagon, right? And then between those 2 corner points, you do the time sharing. So this is a classical, well-known in wireless communication for a very long time. Now, what has been shown by people in EPFL 30 years ago, I think something like this, is that you can use rate splitting on the uplink to avoid having to do time sharing. And so you can use RSMA on the uplink. And so you have, for instance, 2 users. You take one of the user streams and you split into a common, you split into 2 parts. And so one user split is messaged into 2 streams. The other user does not split anything. And so now you end up effectively with 3 substreams. 1 for user 1, 2 for 1 for user 2, and 2 for user 1. And then you can use simple SIC receivers, and you can adjust the rate of the common streams, the rate, sorry, I shouldn't call the common here, the rate of the 2 streams of the user 1, such that you can avoid having to do some form of TDMA. So you can use rate splitting to evolve on the vertex between those 2 corner points without having to do time sharing. And this can have some benefits when time sharing is a problem. Right, so this is where actually RSMA can be used in the uplink.
Thank you, Professor. Next question is, in what proportion does the message splitting divide the original message into private and common messages?
Right, so that depends on the system. It really depends on many things. It depends on your objective function first. So if I take this here, the objective, so here. So this is a weighted sum rate. But if I do just sum rate, so UK is equal to 1 for all the users, actually we can show that you don't need to split the message of all the users. You could split the message of only one user. So that means that the architecture here would be, for instance, you split the message of user 1, W1, into a common and a private part, but then you don't split the message of user 2 to user K. So this is something that you can do if you do just sum rate maximization. If you do weighted sum rate maximization or max mean fairness, then we see there is a higher benefit in splitting the message of each user. Now, the amount of split will really depends on the propagation conditions, for instance. So for instance, the quality of the CSI will influence. The higher the quality of the CSI, the worse the quality of the CSI, there is the higher the power you allocate to the common streams. If you have two channels that are actually more orthogonal to each other, you would have less tendency to allocate power to the common streams. If you have two channels that are actually more aligned with each other, then you would allocate more power to the common streams. If you have a pass loss, if you have small pass loss difference between two users, you would allocate maybe less power to the common stream. If you have a larger pass loss, you will allocate more power to the common streams. So it really depends on the number of users, the objective functions, and the propagation conditions. And you can adjust this depending on what you have. You can adjust this semi-statically. So you may not want to adjust this for each channel realization, or you can adjust this for each channel realization. There is a lot of flexibility there that needs to be investigated, depending on your system constraints.
Thank you, Professor, for thorough explanation. So next question is from Ali. Can you compare the decoding complexity of rate splitting and dirty paper coding?
Right, so if you do dirty paper coding, so dirty paper coding, the problem is in the encoding. So, and that's the reason why it's not so much used at in practice, is because the encoding part is actually quite complex. The decoding part is not really complex, because the decoding, you treat interference as noise. So DPC, you can view this as fully transmitter interference cancellation, formal interference cancellation at the transmitter. The complexity is really there, is at the transmitter sites. And it requires a complicated nonlinear type of precoding. The closest you can come up with something that is implementable is to use Tomlinson-Arashima precoding. But the receiver complexity of DPC is quite low. I would say it's probably the same as SDMA. What you do with rate splitting is that you don't need this kind of complicated encoder here, because you simply use linear precoding, and you have one SIC at the receiver. So you increase the receiver complexity compared to SDMA because you have one SIC. But one SIC is actually what 4G used when MIMO was designed in 4G. The assumption was that one SIC can be used, right? So it's really not something that is challenging. Multiple SIC is something else. Multiple SIC is obviously, it increases the complexity quite significantly, but I think one SIC is not a big deal with current technology.
Thank you. Next question is from Hamad. Is SIC assumed to be perfect for the WSR figure? I don't know which one is WSR figure.
Yeah. Right. So
maybe.
Right. So here, so WSR probably something like this here. Yes, SIC is perfect, and the reason for this is because those rates are always achievable. So if you have perfect CSIT, those rates are achievable. That means that under Shannon theory, if you have infinite block lengths and Gaussian signaling as we have here, because we use those log2 expression, if the rate is achievable, that means actually there is no error, right? If you have imperfect CSIT, then what's happening is that you cannot simply rely on instantaneous rate, you need to rely on ergodic rate. And so the optimization is done in terms of ergodic rate, and ergodic rate are achievable as well. So there is no there is no error propagation because the ergodic rate is achievable. Now, if you have finite block lengths, and so you design the actual whole physical layer, then you may have imperfect CSIC. You may have error propagation because of the imperfect SIC, and this is indeed captured in those link level simulations, like here. This captures the error propagation that you can have in the SIC. Okay.
Thank you, Professor. Next question is a bit different. Pablo asks about what will be the challenging research project for a PhD program in this topic?
Right. So, so here, essentially, for each of those items here, you have problems. And so, if you look at the web page there, here we have we discussed in the best reading, you have really application of rate splitting in many different scenarios. If you look at the expanded tutorial, you have this as well. Essentially, for all the topics I listed here, the application you have rate splitting can be used, and there can be many more. The reason why it's applicable to so many different scenarios is because the communication theoretic idea and concept is very, very fundamental. And so whenever you have an interference problem, the rate splitting or the RSMA can come and play a role. And interference problem is central in wireless. Whenever you have multi-user, you have interference problem. And so, so that's why you can have applicability in so many different scenarios here, right? And many more. And so the overall goal, objectively, you could design an entire physical layer that is entirely based on on rate splitting concepts, where the rate splitting will actually appear in all those different maybe scenarios or actually, yes, application.
Thank you, Professor. Well, we have Prof. Gunesh Kaur from Polytechnique Montreal. She's asking about, can you please comment on the privacy and security aspects of RSMA?
Right. Yeah, that's a question that we get very often. So there are some early work on physical layer security, right? There may be 2 papers that came out in the last 6 months on that. So the problem is actually the same as, so there are 2 issues. There is the security in terms of as it is done now, and then you have the physical layer security. So as it is done now, is not because you decode the message of a user that you actually have access to the actual bits. The bits themselves, they might be, you might have higher layer, you know, cryptographic or encoding that is such that you do not have access to those bits. So in the same way as you do NORMA or you do RSMA, essentially you always have one user will always decode potentially the message of another user or partially decode the message of another user. It does not mean it actually will decode all the final bits that have been encoded at a higher layer using cryptographic or secure protocols. When it comes to physical layer security, this is a bit different. So physical layer security, so security really at the physical layer, the fact that you decode the common streams, so an eavesdropper, if it decodes the common streams, what is left to do is to decode the private streams in order to be able to reconstruct the message. So that leads to some interesting challenges, is what's the role of rate splitting, or how to design rate splitting when you have secrecy constraints. And so you can maximize a sum rate, for instance, but you're subject to secrecy constraints. And you want to make sure that You want to maximize the sum rate, but you don't want to have an eavesdropper being able to actually decode your, for instance, your private streams if he has already decoded the common streams, right? So there are some ongoing works very early there. I mean, all the topics I listed here, to be honest, there's less than a few papers for each of those topics, right? So there is a lot of work to be done there.
Fantastic. Thank you. So Mehdi has two questions, but I believe the first one has already been answered. And it was the question from someone named Shayan. Shayan already answered the same question. So the second question is, when we use hybrid pre-coding, RSMA can be used with fully digital pre-coding?
Right, that's a good question as well. I didn't talk about that. So we have one paper where we do rate splitting on millimeter wave system. And so there we have the hybrid pre-coding. And indeed, you can apply, you can do rate splitting, you split your messages, and then instead of having just one precoder, like one digital precoder, you have a hybrid precoder where you have a first one that is based on analog precoder, then you have a second one that is based on digital precoder with potentially different dimensions. And the benefit there is the following. The hybrid precoder has some constraint because of, for instance, the constant modulus or the fact that it has to be taken from a specific code book. And then the digital precoder may also have limitation because of the CSI accuracy in the feedback. If you have limited feedback, for instance, with a certain number of bits of feedback. And so there, you can use the rate splitting to manage the interference between different users, even in the millimeter wave range. And you can design your hybrid recording accordingly. And so in the power allocation to the common and the private streams. Yes, so this can be done as well.
Yeah, he further asks, how can we use RSMA in higher layers, like in routing? Like, can we use in routing?
I'm not sure about routing because I'm really not an expert on those higher layers. But definitely RSMA can lead to some change in the scheduling. So in the scheduling, you now have the common streams and the private streams. So so what I talked about here was really about, you have your K users that are fixed and then you optimize the physical layer. But we have some examples where we show that rate splitting is less sensitive to how you do the scheduling. So for instance, in SDMA, you need to pair the user very nicely together. You need to have two users that are semi-orthogonal, for instance. Or in NORMA, people pair users in different groups and you have to optimize the group. That leads to huge complexity in the optimizing the groups. In rate splitting, you're much less dependent on that because the physical layer strategy is already quite robust to different user deployment and network loads. But nevertheless, you have some scheduling that comes into play when you decide you know, which user to schedule and so on, and whether you split the message or not. But going all the way up to the routing, I'm not sure. There might be, for instance, in the CRAN case that I mentioned, yes, there might. So here you see that in this example, you have some of the streams, common or private streams. You have to decide whether actually they go on which front-haul link you transmit them, whether you transmit them again. So for instance, you can have some of the stream that transmitted again on multiple front-haul links. You have a whole resource allocation and potentially routing problems there that come into play. That's also possible. Not something that we have really looked at.
Thank you, Professor. I guess the last question is going to be my question, is about the RAN slicing. Like, so with respect to the Crohn's that you mentioned about the complexity in encoding, like imagine that we are going to do RAN slicing, especially for URLC service. Like, how does this rate splitting like can overcome the very limited time to solve such a complex problem in a reasonable time?
Right. I mean, the latency, the latency, the benefit here, which is very early stage, right? The example I gave you here is literally, I mean, it's been on archive for just 2 or 3 weeks. So I think this is the first paper that tried to look at whether RSMA has a benefit in terms of latency. I think the benefit there is really to have the shorter block lengths, which always will reduce the over latency in the system. But it comes with a slightly higher complexity at the encoding, because now you need to have this common stream that needs to be decided. But yeah, again, I don't think this is a major complexity with nowadays network, because if you do polar codes for k streams, or k+1 stream is not that a big deal, I think, especially that nowadays, with massive MIMO, you can serve many users. Whether you serve 16 users or 17 users, I don't think the complexity difference is so huge. So I don't think that, I'm not sure whether there is any significant problem there in terms of slicing, but again, I think that needs to be investigating. I mean, there are lots of cross-layer problem that needs to be looked at, that definitely has not been looked at.
Thank you, Professor Bruno. It was a great pleasure to have you in this event. I hope one day, hopefully after COVID situation, we're going to meet you in person, either in London or in Montreal. So
Absolutely,
it was
a pleasure.
And so just last quick question, and we will approach you regarding the recording of the event, so we will deliver it to you as well. So I received some emails right now from audiences about the recording. Like, can we share can we share the recording in our website or with the registrants?
Yeah, sure, you can do that.
Okay,
feel free to share the recording. Yeah, and then feel free to contact me if you have any other questions. You will see that in the final slide on this web page of this RSMA, we have some common questions and answers. I think that it's always good to read that, because that clarifies a few things. But yeah, feel free to contact me if you have any interest in this, or if you have any questions.
Thank you, Professor. And it was a really, again, great pleasure to have you in this event. And so officially this event has been finished. So if you have further comments or opinion, so we are here to hear from you, Professor.
Yeah, I don't have anything else. Thank you for hosting the talk. And that's it. Thank you very much.
Hopefully we are going to meet one day, Professor. Thank you.
Thank you. Bye-bye.
Have a good day. Bye-bye.